All right, welcome to chapter 12 of Earth History for Philadelphia University. In this chapter, we'll be discussing water resources and all the fun that is entailed with that. As usual, if you have any questions, comments, please leave them down below in the comment section. I or another student will get to them. If you require more information, message me via email, whatever platform, Canvas, Moodle, whatever we're using this month, or again, leave in the comments section. These topics all have a lot more depth to them than what I cover because this is an introductory class. That being said, the stuff's all super interesting. If you find something here you like, let me help you along in your path towards a brighter education. All right, let's start chapter 12 with water resources. 1 second, please. All right, I am back. Hopefully I muted it correctly so I didn't lose a lot of time. Anyways, let's start with water resources. We talk about water resources. I'm connecting back, of course, to previous chapters, the ways we have water here on this planet. This specifically is about the use of the water that exists naturally and as a result of the water cycle, right? Specifically, I'm talking about the concepts of withdrawal and consumption. Withdrawal is a process that uses water and returns it locally. So bring water up, put water back. Consumption would be a process that uses water and returns it far from its source. These two together make up three total usage categories: domestic, industrial, agricultural. And right from that basic assumption, you can probably gather the things I'm talking about here, and also the pros and cons of different ways that we use water in our day-to-day lives. Water usage increases with population, increases with technology, increases with the need of the people. People in our modern life use a lot more water per person than people back 50, 100, etc. years ago. And these graphs illustrate this, right? The agricultural use has risen dramatically, or the amount of water that we use to grow the crops that feed the plants and animals in society has grown exponentially. Noteworthy here is not necessarily the amount of water, but the amount of waste involved. How we define a waste here? Well, let's take a look at this image. Let's try to figure out what that means, right? Notice the left graph of the left bar of the bar graphs is going to always be your withdrawal, or your darker if you prefer color. The right bar of the bar graph is always be your consumption for said given year. And let's go back real quick to our definitions. Withdraw is when you use water and return it locally, i.e. return it to the source from which you drew it from. Conversely, consumption, the water does not return from whence it came. So we are defining waste in this example as water that is not returned to its source. Water that is taken out, used, and then not put back in via how should I phrase this? Via a synthetic water cycle, if you will. Try to think of some examples of withdrawal, and try to think of some examples of consumption, and then take that concept and place them underneath these categories of agricultural, domestic, and industrial. What are you picturing if I say using a source of water for a domestic purpose and then that water feeding back in the system that you started it from? Well, a good example of that would be, right, doing your dishes, washing your hands, stuff like that. The water leaves the faucet and enters the sink, and all cycles back into the same system to be treated and then go back to you again. You're using the same water over and over again. This would be a withdrawal. So you're not reducing the amount of water in the system, you're just using that same water over and over again. Consumption, on the other hand, does not return to the same source, thereby decreasing the total amount of water available. That is why we call it waste, because it is water that is moved in total location via the synthetic or non-natural mechanisms like we have here. And noteworthy here along this path, each of these various definitions, agriculture, domestic, industrial, all have an increase in waste over the past 100 years. And some of these rather dramatically so. Domestic, ridiculous increase in waste, right? Worth of discussion. What does that mean towards water resources that we have available? Is this something we need to work on? Noteworthy at the bottom here, developed countries use much more water than developing countries. That's sort of like a geography, anthropology conversation, more so than a physical science conversation, but it's still worth noting. You live in America, you use a lot more water per person in your household than someone living in a less developed country, say Afghanistan. Everyone's probably going to be drinking the same amount of water, but perhaps you take a nice steamy shower in the morning before you leave. You wash your hands repeatedly. You, big one, probably water your lawn, perhaps. These are the differences we're talking about here. The water supply's demand. What draws from the water supply? A lot of the water supply that we draw from comes from two primary sources, industrial and agricultural needs. Domestic water use is high, but there's a big difference between the amount of water it takes for you to shower and the amount of water it takes to work electrical power plants, coal, oil, solar, what have you. If water is turned to steam to turn those generators to power the electricity, that's a lot of water that has to be used in a given moment. So much so that 3/4 of all industrial water demand goes towards power production, and half of all water use is incorporated into that 3/4 amount. The other roughly half of water goes towards agricultural, right? Growing crops. So while you as individual, your water usage is a small subsect of this number, it's also not negligible. 10% is still a lot of water use on a domestic scale, right? And understanding these various principles, these different approaches to water use, water waste, what have you, dictate the world that we live in, because water is a part of everything, right? Domestic, agriculture, industrial, all use lots of water. Working these principles together to, say, reduce that waste component is vital, is key, is something that needs to be discussed. Here we have a picture of exactly what I was talking about, agricultural water use. Water is sprayed out onto the crops in these very imprecise mechanisms, right? Spray irrigation, the spinach field showed here. Not every single drop of water necessarily interacts with a plant to help it grow. Water gets caught up in the wind, water evaporates on the surface before the plants can get to, et cetera, et cetera. You not have 100% usage of your water on planting these crops, as opposed to, say, watering a potted plant in your house. You have better control of that water. You know how much water is going to your plant. These spinach plants may individually require less water per plant, but you need a lot more water via the mechanism that the water is being spread out by. You therefore need more water to come up to cover those losses via evaporation, wind, bugs, what have you. As shown here, we have a nice graph and chart explaining the rough percentages and amounts of water used per day. Here, 2015 withdrawals by category in billions of gallons per day. And it's, again, amazing to look at and understand how this works, right? Thermoelectric power shown here. That's basically any electricity that's not directly connected to the generation. So we're talking not hydro, not wind, and not photoelectric cells, solar. Any power electricity in 2015, they used 133 billion gallons of water every day, according to this USGS survey. That's amazing, right? And Noteworthy here, irrigation right behind that conversation. 118 billion gallons of water was sprayed on plants to help them grow every single day in 2015 estimate. And again, I'm going to stress here, this is what we're talking about when we say irrigation. Wherein of that 118 billion gallons, that's not 118 billion gallons going to the plants. That's 118 billion gallons that have to be sprayed in this industrial fashion in order to get the spinach the amount of water it needs. As I said before, public supply, 39 billion gallons. That's still a lot of water, a lot more than any other lower level amount, such as aquaculture, self-supplied industry, mining, livestock, what have you. Big amounts of water being used at any given moment here. And we can see a trend in population fresh water withdrawal going up and up and up, right? We do have some dips showing here in total water usage. Why do you think that is, right? Why are we using less surface water? Groundwater has stayed more or less consistent, but why are we using less surface water to get stuff done? Could that possibly be technology? Right? Interesting conversation to have. And I guess I should point out on this graph over here, we have the withdrawal of water, and over here we have the population. So we have two different y-axes flowing here. As the population increases, we do have a decrease in water usage. Interesting. Here we have a fun map showing the water use per gallon per day per person and population and per percent population growth in 2015. This is domestic water use. Noteworthy here, we have some outliers. Michigan's not 0%, right? We use water in Michigan, but we have some places that seem kind of surprising, right? Idaho, massive amounts of water. Nevada, massive amounts of water. Why do you think some of these places have such high amounts of water? The answer to that, well, what is this climate like, right? This is a desert climate. People are using a lot more water for just regular keeping yourself, keeping your thirst quenched. There we go. That's what I'm looking for here. But also things such as if you need to water your lawns, you want to have a green lawn, you're going to use a lot more water for that domestic purpose. So we roll over here. We have less water use again as we're getting to more precipitous climates where water is not such a hard thing to come by. But then again, we can roll out over here, Delaware, District of Columbia, what's that? Virginia, North South Carolina, right? A lot of water use going on here. The map is not necessarily obvious, which is interesting. Why is some places have more population than others? I mean, more water usage than others. Good questions to ask yourself. This chart here, again, going into usage of water, we're going to switch from domestic to industrial. How much water is required to make said product? Notice down here, a kilogram of steel, not really a whole lot of water involved in a kilogram of steel. Kilogram of paper, 4 times the amount of water. That's impressive. Steel and paper, both a kilogram worth, use a very disparaging amount of water. And then we can run up here to aluminum, 9,000 liters of water needed to produce 1 kilogram of aluminum. That's intense. That's very, very intense. 1 kilogram of synthetic rubber, 5,000 liters of water. How much rubber is there in the tires of your car? Think about the water usage involved in that. And again, I want to stress, there is a conversation of consumption versus withdrawal. So not all this water necessarily is not returning to its aquifer source, but we do have that component to consider. Again, we can go here, we can look at the agricultural side of that same conversation. A kilogram of cotton uses massive amounts of water as opposed to, say, a kilogram of corn. cotton, however, is very readily used in our day-to-day society, day-to-day culture. We need a lot of water to make that work. Rice, corn, loaf of bread, what have you. This is just for a kilogram of this. A kilogram of grass-fed beef, 7,000 liters of water. A kilogram is 2.2 pounds. So when you go to the store and you get one of those 4 or 5 pound tubes of ground beef, right? That's like 2.5 kilograms. So you're talking what, 18,000 liters, someplace around that, of water just to make that tube of beef. And how many other tubes of beef are there on that shelf in Walmart right now? Things to consider. What is the water usage? How are we using this water? Do we have a limited supply of fresh water? No. Go back to those previous chapters. The vast 97.5%, I believe, of water on this planet is salt water that you cannot use for these purposes. And then within that 2.5% of fresh water, majority of that's in ice, which again has its own purpose, which we'll talk about in future chapters when we talk about glaciers. Groundwater and freshwater are a small minority of the total water on the planet, yet the usage is tremendous. This image here shows the risk to quantity of water, how much water you have, and the usage requirements of it. And we notice this kind of flows with biomes of deserts and mountains and stuff like that, but it also works with populations. Notice, for example, let's look at this spot here. What are we looking at in this particular part of the United States? Well, that's Detroit and Chicago, basically, right? High risk of quantity of water loss in this area because a lot of people are using the water, and a lot of people are using it perhaps flippantly, perhaps in ways that, if they stopped and thought about it, could be better used. Sure, you're going to have this problem, say, in the Sahara here, in Saudi Arabia, Yemen, Oman, Pakistan, Iran, what have you, where we have more arid climates, less precipitation, less natural water, refilling the aquifers, what have you, of the ground. But China is basically on this high risk, extreme risk conversation too. Again, this is a combination of agriculture, industrial, and domestic water use. And it's not good to be an extremely high risk chance of not refilling your water supplies, running out of water, the consumption of the water. So dams and diversions. We talked a bit about how we use water. How do we get water to places where we need to use it? Well, we could talk first about diversion systems. These are your pipes and canals that transport water around. Technically, the water pipes in your house are a diversion system. The water comes in from a central source, usually a water pump, perhaps in your basement. That's all the water comes in. And then from that one pump, water is pressurized to every spigot, every hose, every source that you have in your house. You don't have a cistern anymore. You don't need to go out to the well with a bucket to collect your water for the day. You have water 4 or 5 places throughout your house that have access to. Your washing machine has water, your dishwasher has water, et cetera, et cetera. And this diversion system also works if you have city water, for example. The entire neighborhood is also connected in this exact same concept. You can see where the separation between water withdrawal and water consumption happens here, can't you? Another thing we can do with water is we can dam it. This is trapping and storing seasonal precipitation. This could be in the form usually of building a dam on a river to turn the section into a lake to control the flow of that river. We talked about river flow and river speed earlier. There were about 57,000 dams in use in 2018, all varying shapes and sizes. We're not talking beaver dams here. We're talking industrial-sized dams. Not all of them necessarily for hydroelectric use. Of course, America, Hoover Dam is a good example. But Hoover Dam is kind of dwarfed in size by some of the other dams in the world. The Three Gorges River dams in China are massive. And they really have an effect on water use and water consumption. Those dams represent about 60% of global energy consumption, global electric consumption, and they offer competitive energy production. But usually the main point of the dam is something other than energy production, although energy production is, I will definitely grant, a very large part of the conversation. What do you do when you dam up water? What do you do when you divert water in different locations? You can have water loss, right? Water loss occurs when the water in reservoirs evaporates or infiltrates into something else. Less water flows through river systems, etc., etc. This is always a conversation because the water cycle is going to happen regardless. Water on the surface, when the sun cooks it, it's going to evaporate up. Water on soil is going to drain down, maybe into an aquifer, maybe rotate itself back into a lake or river nearby, what have you. But that water loss is still part of the game plan that you need to discuss when you talk about water resources. And of course, we could talk salinization. This occurs with long-term irrigation in dry climates and involves the dissolved load of the salts in water that build up in the soil and add that salt to the soil, which therefore lowers crop yields, makes the soil less effective. We talked about soil before. What are the components of soil? Components of soil include nutrients that plants want. What do plants not want? Lots of salt. These are conversations you need to have in this process of water resources, how they work back and forth with each other. Here's an example of white salts that cover vast expanses of the Nevada desert. The salinization has reduced the productivity of millions of hectares, millions of cubic meter of square kilometers of agricultural land globally, due again to the way you treat the water, the withdrawal, the consumption, the return of the water to these various localities. All right, let's get a bit deeper into this conversation about dams and diversion. Let's talk about silting. What is silting? Silting is the sediment deposits that happen in reservoirs. This is the production of the river or lake bed where you're holding the water. It's going to naturally fill in over time, like any river or lake would do. That sediment can, of course, erode downstream of dams, perhaps causing changes in the river flow, the river production. Dams, of course, can fail. That's something you need to keep in mind. It's not very common, but it's also very catastrophic when it happens. And what happens when you dam up a river? Well, you're affecting the ecosystem of that river, both the natural ecosystem, the fish use, the bird use, what have you, but also the human aesthetic use of it. River's a lot less exciting. Maybe people aren't going to go there as often, right? Aesthetic losses, dams can flood landscapes, create new floodplains, push people out of their houses and homes. Look up the construction of any major dam sort of before the 60s, then you'll hear and you'll read stories about people losing their property and stuff like that because the dams make where they've lived unviable. Right? All these images that can happen as a result of us harnessing the power of water. Dams bursting, dams breaking, rivers changing, areas flooding, what have you. As I said before, there's ecological disruption factor when you affect water flows, natural water flows we talked about last chapter. Changing river valleys can alter lake biota. These, of course, can have a massive cost not only on the flora and fauna of the area, but also the human involvement with it. Dams have negative effects. Of course, dams also have positive effects, right? Cool. Groundwater diversion. Groundwater is, as we've talked previously, the vast majority of the fresh water that we have on this planet is held up in the sediments and soils that we have as groundwater. Most of our water comes from there. I guarantee you, your house is probably fed by a groundwater source. If it's a well, obviously it's groundwater. If it's city water, very, very high chance. Even up here in the Upper Peninsula, where we're surrounded by Lake Superior, very high chance that groundwater is the source of your tap. But as we talked about previously, and you probably remember from your physical science class in high school, groundwater depletion is a very real issue via usually overpumping, cones of depressions, aquifers simply not replenishing as fast, etc., etc. Remember, how the water table fills is water hits the surface, and hopefully if the surface material is permeable, water can transport through and go down into the water table where it fills up because some underlying bedrock is unpermeable. And then this stuff is porous, right? That's the conversation we had. But when you use the water, it's a lot faster to use water than it is to return water. Pumping water out of the ground with a well pulls a lot of water a lot faster than it takes the water to slowly move through the sandstone over time down to reconnect and fill up the water table. This is a seasonal conversation, of course. During the spring, a lot of the soil's very moist with water, but say during the fall, during the winter, you don't get this refill, but we have continuous use. Here we have an example of an aquifer shown here, and it's associated water table. Here's a picture of it in Nebraska, Kansas, Oklahoma area. And we notice, based on usage, this gigantic aquifer that sits in this bedrock, down here at the bottom, we are having reduction of the water that's available from said aquifer, right? You have a west to east. So this picture here is going west to east, like this, just so you can kind of gather. It does not look like this is a actual line. No, it's not. Okay. So what we have here is if you have a lot of consumption of this aquifer, say, do we have any cities in this map? I guess we do not. If we have a lot of consumption of this aquifer in certain localities, that affects the surrounding area. You have a lot of withdrawal in, say, will that be southwest Kansas here, northeast Oklahoma, the top of Texas. That's probably, I'm going to guess, a lot of farmland up there. They withdraw a lot of water to water their crops down here in North Texas as well, by New Mexico, or I don't think it's a seasons area. A lot of here to water the crops, reducing a lot of water for all of this area. All of this area has loss of water. And furthermore, let's contrast areas of decline to areas of rise in the water table. Look at all this reducing down. Look at these little tiny bits in the corners here, building it back up. The water table is shrinking by usage, by lack of return of the water. What happens if you continue to pull out the water? Well, the water holds a physical space in the soil, right? That's what the water does. It's physically there. It applies pressures or what have you. If you pull out enough of that water, or I guess you could argue oil, gas, what have you, you can have subsidence. Subsidence is the ground dropping down, the ground sinking in. The sinking of the Earth's surface is caused by loss of aquifer porosity, caused by the removal of that water that's in between those grains. Those grains can squish together more, causing sinkholes and what have you. If you are near salt water, you can actually get saltwater intrusion into these zones. This is fresh water. The assumption is made. This is a freshwater aquifer. What if you have subsidence? What if you have removal of this area here such that saltwater can get there intermix, and now you're pulling up saltwater with your pump? You don't want saltwater at your tap, right? Conversations to be had. Here we have a perfect example of science, very famous picture from the USGS here, showing the San Joaquin, California, I'm going to pronounce it as, with the height of the land surface in 1925 was all the way up here, ridiculously tall area. And then it's been dropping ever since. And why do you think it's dropping? Well, look to the side here. What is this? Farmland. They're pulling the water out of the ground, and the ground is responding in kind and reducing its elevation. And that is a massive drop. This picture was taken in 1977. How low do you think this ground is now? Right? That subsides and underlying aquifers are depleted. Does it rise again? Well, what do you think? Right? Here we have an example of the saltwater intrusion that we were talking about before. You have a pump here pulling out water. As the freshwater table subsides, the saltwater table eventually will be poured in, giving you water that's not useful for your domain. In this example shown here, we have a recharge well as well as a pumping well to essentially read a little cycle of water in this location and keep the salt water out. Real, actual, viable concern. If you excessively pump the water, so much of the water table can't handle it, you deal with the consequences. In this case, salt water, not good. We have in America, for example, a Great American Desert, but this is a conversation that most every continent on the world can also have. We're just going to talk America here because, let's face it, book is published in America. Most of us are probably most familiar with these concepts. Great American Desert, between the Western Mountains and the 100-degree meridian, mostly arid or semi-arid, but very populous despite lack of precipitation. Think Phoenix, Arizona, as an example. Literally in the middle of the desert, right? Billions of dollars are spent each year on water diversion, moving water from where it naturally is to where people want to live. The Colorado River is a fantastic example of this. It has been apportioned to states that the Colorado River does not necessarily run through. The water does not reach the sea to replenish that water cycle, thus making things very salty, affecting rainfall, affecting reservoir levels, affecting droughts, what have you. And we're talking about people living where there is no water, moving water to them. That takes energy, that takes resources. I can go back, right, to these pictures of how much water is used in the production of the materials that it takes to move the water to places that people live at currently, right? Self-fulfilling prophecy. This is a cycle of questionable idea after questionable idea after questionable idea. I say that as someone who, let's be honest here, lives in a very water-rich part of America. So, I can look down on those people in Phoenix and say, look at all the work that has to go through to give you a nice green lawn. But it's still a conversation to be had. This conversation of what to do with water. Water is, of course, the key resource in human life. Affects other countries as well. I said before, the Jordan River would be a fantastic example of this. The Jordan River runs through many countries that don't necessarily work very well with each other. So if, let's say, Syria plans on damming part of the Jordan River and divert water from the Jordan River to Jordan instead of going to Israel, forcing Israel to perhaps pump out its own aquifers harder because it doesn't have the water from the Jordan, this gives you an issue. The Nile River is another fantastic example of this. We associate the Nile River with Egypt, but the Nile River stretches very far south beyond Egypt into Sudan and other countries. I think it starts like in Ethiopia. So if someone upstream of the Nile River, or the Jordan River said here, or the Colorado River, wants to use those water resources, that affects everyone downstream in proportion. And as said here at the bottom, important note, there's no international code of water usage. There's no grand conversation about how we use water, even though it is without question the most important resource to humans. Interesting conversation, right? Water pollution. You talk about water use, you got to talk water pollution. Water pollution is the reduction of water quality. There are many stories, go look it up, of rivers catching on fire because they're so polluted. A river on fire. It doesn't make sense, but it used to be a not uncommon thing. You used to not be able to swim in some of the rivers of large cities because they were so highly polluted. You still can't in some parts of the world. This happened mostly during the Industrial Revolution when people didn't really care as much because arguably people don't know as much the impact that pollution has on our water resources. In 1972, the Clean Water Act, there's a Clean Air Act as well. The Clean Water Act was implemented to promote clean water policies and sources and to clean up essentially the water of the United States. And it's been more or less effective. A lot of waterways that your grandpa refused to play in because it smelled so bad, you can go take a swim in nowadays due to these regulations. Right? Does that look gross? There was a time in American history where this was the norm. Pollutions, garbage, dumping of waste, what have you. There's 5 or 6 Simpsons episodes about this stuff happening with Monty Burns, right? The Clean Air Act has quelched a lot of these issues. Here is a river that's on fire. It's crazy, right? This was a major concern 50, 60 years ago. Nowadays, not so much because of regulations such as the Clean Air Act. What kind of pollution do we get in water? Well, first of all, we can talk about biodegradable pollutants. These are pollutants that, as it says here, biodegradable, decays naturally. Food waste, human waste, soaps, things along those lines. Things that you don't feel as bad if you throw it out. Most people, I'm sure, if they eat a banana, throw the banana peel outside the windows and drive down the road. Because in a few days, that banana peel will be decayed and it won't be there anymore. Not quite as big of a deal. Take the sticker off first, usually. But even the stickers are made to be biodegradable. The problem, well, biodegradable pollutants are an issue. A bigger issue would be non-biodegradable pollutants. These are things that do not decay naturally, such as pesticides, mine waste, sediment, PBTs, what have you. These guys can cause an issue. If you live in the Kappa country, like I'm sure some of you do, that go to Finlandia, you will know that we have mine waste throughout the area. There are peninsulas built with the waste rock from the copper mining in the area, and that waste rock has had a significant impact on the waterways we have around here. You can go talk to people that live on Torch Lake, and they'll tell you when they were kids, no one ever swam in Torch Lake because it was so disgusting. Beyond non-biodegradable pollutants, we can go a step further, and we can say we have radioactive pollutants, radioactive materials that enter the water stream, such as the mine and waste from radioactive ores, nuclear power plants, things along those lines. The heat itself can be a pollutant. In my hometown, we had an oil power plant that was so pollutant to the local lake that we had deformed fish with fins coming out of their faces, fish that were like growing proto-feet, because mostly the water that came out of the power plant was so very hot, it was messing up the environment in the area. We actually had an infestation of piranhas somehow in the lake. And this is in Michigan. Right? Beyond these conversations, of course, we have point source pollution stemming from a specific site. You are not allowed, for example, to build junkyards on near sources of aquifers of water, because if you do not contain the pollutants of the junkyard, they can enter the water source and cause damage to the surrounding area. All gas stations are built on top of concrete bowls, essentially, in case one of the tanks ruptures, the gasoline is not going to seep into the local water supply. And from beyond point source pollution, we also have non-point source pollution. This is the broader idea. Large farms have this issue wherein if you have a large swath of many farms in the location, that entire surrounding area is going to have some sort of pollution from fertilizer, pesticides, what have you, but you can't exactly point it back to a specific farm, because all the farms are using these things, all the farm water is being recycled back in, causing these issues. A lot of conversation to be had on this topic. A lot of conversation. Again, if this is of interest to you, please leave a comment. I'll take a look at it. Maybe we can work to finding you more interesting information on it. So, talked about those pollutants. Let's go a bit deeper into that. How does sewage, detergent, and fertilizers pollute waterways? Well, pollutants are nutrients. Pollutants increase O2 consumption of organisms. And all that O2 is then consumed by anaerobic bacteria, which can release, for example, hydrogen sulfide. So you're you're kick-starting some natural, some artificial, some natural processes that will become out of flux with the environment. The decay of these organisms die as the pollutants are consumed, and you have a natural turbulence that tries to replenish the O2 amount. What you have is a natural stability of the waterway, and then you throw a wrench in that stability, throw it all off kilter. the waterway will eventually return, yes, but at what time and how is that going to affect the people around it? That's the conversation to be had here. Some compounds, as said here, can persist in the environment. Not everything will be necessarily washed away in a timely fashion. Of course, we can go back and talk about radioactive materials. Radioactive materials can stick around in the water for quite a bit, can be swallowed by fish. I'm sure we've all heard conversations of pregnant women and young children cannot eat seafood that's caught wild in the ocean because of the amount of mercury in the fish, due in part to these conversations. The effects of these dosages sometimes aren't quite as well known, but this is still a primary concern. Pollutants and pollution control have a very large effect on humanity as a whole, right? Because again, water is the top resource of mankind, and water is also easy to pollute if you don't care. And on top of that, the externality of pollution control is an expensive thing to fix. It is a problem that is easy to overlook because the effects are long term, and it's hard to fix again because the effects are long term. Additional unintentional consequences of the original activities. Groundwater pollution follows all the same principles as surface water pollution, which we've been talking about, giving examples of. Just you need to take into account the water cycle and the seepage of the water down, right? This groundwater pollution would be connected, as I said, with those gas stations. Most gas stations, the tanks that hold the gas under the surface are held in concrete domes, concrete bowls, so that if there is a spill underground, you don't interact with the groundwater, because what happens? Gasoline gets out, interacts with the porous, the permeable soil around it, and it seeps just like water does, except that gas is less viscous than water and flows faster. Gasoline spreads, gasoline gets everywhere. Now, all of a sudden, your water has trace amounts of gasoline in it. Go to YouTube, find pictures of people in Flint, Michigan that can light their kitchen sink on fire because of the pollutants in the groundwater have seeped into the system, creating these issues. Very hard to clean out this water, right? The groundwater, this aquifer, these things can be massive. And sometimes it doesn't take a lot of pollution in your aquifer to hit that crucial point where it becomes unattainable to use. You can have plumes of contamination. These are the zones within aquifers affected by the pollutant. Sometimes the pollution's concentrated, sometimes it's spread throughout, depends on the pollutant. Contaminants can persist longer in lakes and streams due to slower flow. So you can get that pollution going from the groundwater into the lakes, sitting there, holding there, recycling back in. And of course, you have less O2 in the groundwater as a result. All of these here are examples of exactly what we're talking about here. Sewage treatment plants, landfills, crop dusting, your septic tank. Here we have an example of leakage from a lagoon, a industrial lagoon, right? Look at the size look at all these plumes of pollutants coming down, heading towards the water table. This blue line here. Here's the water table. All of these sources pollute this water, and if you draw from this water for literally any purpose, you're going to have to deal with those pollutants. Obviously, for domestic purposes, you don't want to drink polluted water, but even for agricultural purposes, you don't want to put polluted water on crops. And industrial purposes, you're running water that's heavy in metals, for example, that's going to corrode, that's going to damage your machines. This is a problem that affects literally every component of our lives. Here are examples. Here's a list of the average residence time for water in various reservoirs. How long does water stay in these locations? The atmosphere, clouds, what have you, water doesn't stay up that long time, right? Rivers flow, water gets away from it. But it doesn't take very far down this map to get very long lifespans for water in location. If that water is polluted, there's a good chance it's going to stay there, right? Shallow groundwater, that we're talking like the well at a farmhouse. That water could have been down there for hundreds of years. If that water was polluted when it got there, it's been sitting there for hundreds of years, not moving, not necessarily breaking down and going away. Deeper water, tens of thousands of years, right? So in this leaking gas tank, because they didn't put the concrete bowl around it to prevent this leak, flows down through this permeable soil into the groundwater, and flows on through, mixing in here. If this is deep enough, you're talking that gasoline's going to be there for thousands of years. This is an anaerobic environment, not a lot of oxygen to interact with bacteria to break this stuff down. Not necessarily anaerobic, but low oxygen environment in this aquifer. This gasoline doesn't have any place to go. And it's, again, gasoline is less viscous than water. It's going to flow through. Maybe this groundwater is going to a lake. Now you're affecting the lake. So how do you treat a contaminated aquifer? First, most important thing is eliminate source of pollution. If you have a leak, if you have a source of contamination, you need to cut the contamination off so it doesn't continue adding. Once you have cut off the source of the contamination, you need to constantly monitor what's going on with the problem here. Is this something that is naturally going to fix itself in a short amount of time? Is this something where I need to get involved? If you do need to get involved, you can look at the bioremediation, using microorganisms that will eat the pollution, or perhaps chemical remediation. Do I have to put something in the water to neutralize said contaminant? Bio and chemical remediation are both very expensive. Over 2,000 metric tons of heavy level radioactive waste is generated every year in the United States alone. We're not the only people making radioactive waste. What do you do with that? Right? I'm sure you've learned about in science classes past, half-lives, radioactive decay. Some of the radioactive waste lasts tens of millions of years. You need a permanent repository for this radioactive waste. What are you going to do about that? You can't, right? In the past, radioactive waste would go in the water supply. It doesn't go anywhere. You can still pull fish out of the ocean that have trace amounts of uranium, plutonium, what have you, in them, because the radioactive waste doesn't go anywhere. So what do you do with this? And what if you build a repository to hold this radioactive waste, and you happen to build it in a place that's prone to landslides, which we've talked about in the past, right? Steep slope, big flow of water, landslide comes down, breaks it open. Important conversations to be had, very important conversations. So let's look at the Clean Water Act, discuss that before. The Clean Water Act was intended to do exactly what it says, clean the water. Municipalities and factories could no longer dump raw sewage or discharge untreated water directly into waterways. Before the Clean Water Act, that wasn't illegal, partly because we didn't know the full extent of it. The science wasn't exactly as crystal as it is now, partly because, again, you're talking about just a general not caring. The guy that owns the plant don't live next to the plant. So what do we do about this? The sad fact of the matter is the Clean Water Act needs to be enforced. Business owners aren't out of the goodness of their heart going to spend more money on something that doesn't produce more profits. The Clean Water Act is only going to go as far as, you push it. In 2008, the EPA, Environmental Protection Agency, found 49% of U.S. lakes contained fish that were contaminated with mercury and unsafe for human consumption. Half of U.S. lakes in 2008, that's not long ago, half of U.S. lakes were not producing fish capable of human consumption. That's not natural. These lakes do not naturally produce fish that can't be ate. So if it's not natural it did it, it's probably artificial, right? 2009 New York Times study found over 500,000 violations of the Clean Water Act occurred in the prior 5 years. 500,000 violations. And what is a violation? Dumping raw sewage and discharging untreated waste directly into waterways because it's cheaper. Water is the key resource that humans use, and over 500,000 violations found in the 5 years previous to 2009, not 1975, 2009. When everyone can agree we don't want rivers on fire anymore. I mean, I'll go back. Let's look at that picture. Look at that picture. That's not from Stranger Thing times. That's not the 80s. That's not the 70s. That stuff happens today. Well worth your time to understand these concepts. This is a politically charged issue to this day. What do we do about this? How do we keep water accessible, not only accessible to people, but also healthy for people? If you'd like to know more information, please leave a comment below. If you are interested in this topic, let's have a discussion on it. This is well worth your time having a discussion on. Being educated in these concepts is only going to help you. Thanks for listening. Hope you enjoyed the chapter. If you got any questions, shoot me an email, comment below, and take care. Stay safe out there.